Thank you very much. I'm going to talk to you about our 5-qubit ion trap quantum computer. And this is sort of an overview of the system. This is what a computer scientist would call the stack. The basic idea is if you want to execute any kind of quantum algorithm, they typically come written down as a circuit of computational gates such as Hadamard, C-naughts, and so on, which you can then break down into gates that are native to your hardware. And these are then implemented using some classical control, in our case laser pulses and so on your actual physical system, which in our case is a chain of ytterbium ions. And I'm going to just go through this from starting at the bottom, going all the way to the top, and I'll give an example of one algorithm, which is the QFT, which we have implemented. And then at the end, I'm going to talk a little bit about architecture and quantum computing design, which has been sort of come on the agenda because of the recent IBM cloud quantum computer that went online. And so I'm going to talk about that a little bit. Okay, this is sort of my artist's impression of what our system looks like. There's a lot going on, so I'll sort of describe this starting in the middle. What you see here, these dots, they are single ions of ytterbium-171. And the reason we like ytterbium-171 is because it has this pair of magnetic field insensitive states in the ground level here, which make a very good qubit with seconds coherence time without trying terribly hard. It also has an easy scheme for state preparation by optical pumping and state detection by state-dependent fluorescence. And to manipulate this qubit, we use a pair of Raman beams at 355 nanometer. This is sort of an industrially relevant wavelength, so you can get very stable and reliable laser sources at high intensity at this wavelength. And we use a pair of these to drive Raman transitions between these two qubit states. And so these sort of generate a beat node that then drives the qubit between these two computational states. And the way these are applied to the ions is we have a counter-propagating pair of them. One is this global beam that comes in from the top left and hits all the ions. And counter-propagating to that is another beam that is split into 10 individual beams, each of which is matched onto a channel of this multi-channel AOM, which is basically a switch, if you like, for individual channels, and then focused onto single ions. And that means we have one addressing beam per ion, and that means we can sort of selectively manipulate the qubits. This picture does not show ions. It shows rather what these beams look like at the place where the ions are. So this was taken by trapping a single ion and then moving the beams across it and use it as a point detector of light, if you like, to map out what these beams look like. And you can see they're reasonably nicely shaped and separated. If you look closely, you can see some aberrations here, which means addressing will not be perfect. And this is some data that shows the crosstalk, and neighboring ions are addressed with better than 2% and non-nearest neighbor with better than 1% addressability. So that means we can address individual qubits. The other thing we need to do is read them out, and for that we have these detection optics over here. So this picture actually does show ions imaged on a camera. But for all the computational purposes, we image this chain onto a multi-channel photomultiplier. It's multi-channel. That means every ion has its individual photodetector. So you can see this here. These are the channels. These are the counts. So we image on alternate channels. So we have one photodetector per ion. And that means we can read out all of the different states that this 5-qubit system presents. And that's 2 to the n. That's 32 different states. And you can see the readout fidelity for each. It's best for just all zeros because the readout fidelity for a zero state is pretty high, about 99.7%. It's only about 99% for the bright state. So this 1 state here has about 95%. And there's some here which are even lower, like this 10101. And that's because there's some crosstalk in this device, which means that there's some spillover from a bright ion to a dark neighbor. But overall, we can read out all these states with reasonably high fidelity. Okay, so that's sort of the hardware. What are the quantum operations that we do? Of course, the first is single qubit rotations. And I talked about this Raman beat node earlier. If we apply a resonant beat node at the qubit frequency, we can drive Rabi flops. And here you can see an example for all 5 ions. So we're going from state 0 to state 1 around an axis on the equator of the Bloch sphere, and this is what we call an R gate. So this has two parameters. One is theta, which is the pulse area, if you like, and phi, which is the phase of the beat node that we can also control. Okay, this is almost all the ingredients for a quantum computer. We can initialize, we can do some manipulations, we can read out. What we're still missing is 2 qubit interactions. And the way we bring those in is we use the motion of the ions in the trap. So if you drive your qubit at a resonance here, like I said earlier, if you set the beat node to resonance, you get these carrier transitions, or these Rabi flops. If you detune by a motional frequency, you get sideband transitions. So the ions are trapped in this harmonic well, and that means they, in addition to the sort of spin degree of freedom that we use as the qubit, they also have a motional degree of freedom, which are these ladder. It's this ladder of Fock states of the motion, and the sidebands basically correspond to adding or subtracting a phonon. Now, obviously, we have more than one ion. We have 5, so we have in general 5 modes. I'm just showing the first 2 here. And all the ions are interacting with all of these modes, and that means the motion can act as a quantum bus to transfer information from one to the other. Now, how do we make a gate out of this? We use this so-called Molmer-Sørensen scheme. Basically, this is the Hamiltonian. You can see there's some motional terms, spin, and there's a prefactor here, which is called the Lambdicki parameter, which is essentially the ratio of the sidebands to the carrier. And you can see there's a delta k in here, and that is the difference in k vector between the two Raman beams, which is why it's advantageous to have this counter-propagating geometry, because that maximizes this factor. So if we simplify this a little bit, you can see we're left with 2 terms. One is this spin-spin term, which is what we want. And then there's also a spin-motion term. So this d is a displacement in phase space. We're basically driving a harmonic oscillator mode off-resonant from, off-resonantly, which means we are exciting and de-exciting the motion. And so in this Molmer-Sørensen scheme, we have 2 frequencies, which are, so it's a bichromatic tone that is detuned from the motional modes. I drew it sort of on the outside here, but it can also be anywhere in between those modes. So the effect of this is a displacement in phase space that is spin dependent. There's a spin term here, and that means we drive these loops in phase space. And of course, at the end, we just want a spin-spin interaction. So we want to get rid of this first term, and we do. If you just have one mode, it's easy. You just stop at the appropriate time. You close this. Displacement goes to 0, and you're left with a sort of phase chi-ij that you can choose by just choosing the size of these loops. Now, of course, we don't just have one mode. We have 5 modes. And the detuning for each of the 5 modes is different. So that means these will go around at different rates for every mode. And that means rather than just having this simple solution, we have to fulfill 2n plus 1 constraints. Each of the n alphas has real and imaginary term. And we want to set this value to something of our choosing. So we need additional knobs, additional parameters to do this. And we get these additional parameters by breaking the gate up into several segments. And we do this by basically changing the power of the global beam during the gate. And we break it up into segments and have a different Rabi frequency or different intensity of light, if you like, in each segment. And then you can pre-calculate a solution that closes all these loops in phase space. So this is an example. We're putting a light on ions 1 and 5. We're detuned between modes 2 and 3, which is why these loops are the biggest. And you can see by employing this scheme, all of these close at the end of the gate interaction. And so we're left with this spin-spin interaction term, which is what we want. So if we do this, this is sort of the unitary that we're left with. It's what we call the XX gate. And if we choose this phase appropriately to be pi over 4, then we get this maximally entangled Bell state. And we can check how well we perform this by doing some parity oscillations. And we do these gates typically with 98, 99%. So reasonably well. And the nice thing is, because we have this arbitrary addressability, this constitutes a fully connected system of 10 qubits. So we can invoke each of these connections selectively just by turning on the appropriate beams. So this is sort of going to be, remember this picture, it'll show up later when I talk about architecture. Okay, so now this is sort of our native gates. How do we make computational gates? The C-NOT gates is sort of a staple controlled NOT gate. And you can make it by surrounding this XX gate with some individual rotations on the ions, and you get this C-NOT gate. Now we have 10 2-qubit interactions. That means there's 10 C-NOT gates, and here they are. Similarly, for the C phase gate, controlled phase gate, you have a different set of individual rotations, and we're using the fact that this chi-ij is sort of a continuous parameter in our entangling gate. And so with that, we can construct these controlled phase gates, and again, there's 10 of them, which we can show. In order to analyze them, we start with a superposition on one of the ions, then do the controlled phase gate, and then do an analysis pulse to show that this works for all of them. Okay. Now, that was sort of a quick run-through of the lower 3 tiers here. Now on to quantum algorithms. I'm going to show sort of the most involved or complex computation that we have implemented, which is the quantum Fourier transform. And the way you would normally use a quantum Fourier transform in a sort of quantum computing context is you have some kind of controlled unitary. For example, if you're doing Shor's algorithm, this could be modular exponentiation. And then you do a QFT on these ancilla qubits over here. And that tells you something about this unitary. So we are not doing this gray part over here. We're just trying to see that if we can do the QFT and how well it works. This is the circuit. You can see it uses all the 10 different 2-qubit interactions that we have. And what we do is we just prepare a state here and we analyze it using the QFT. I'm going to show 2 examples. The first is period finding. So if we prepare a state with a certain periodicity, so this is period 8, you can see 7, 15, 23, and so on. We can prepare this just with single qubit rotations, and then we run the QFT. The output is a state that has 8 peaks, and that indicates period 8. And we can repeat this for various periodicities, and you can see it works nicely. You get the right answer. Interesting, I want to point out this result here. This is period 1. So here we start with a superposition of all 32 input states, and we get this 1 peak. Of course, wherever that peak appears indicates period 1. So the difference between it appearing here and somewhere else is sort of the phase relationships between these input states. And so that is the basis for the second example of the QFT, which is period finding. So we can basically do the same thing, but we change the phase relationship between these 32 input states. And so we set up a state like this that has a phase factor over here. And then we run the QFT, and you can see the answer that we get is that phase as a 5-bit number. And so there's a 1-to-1 correspondence, which is why this is diagonal between the phase and the output. And if you go to 2 pi, you go back down to 0. Okay, and so this works with reasonably high fidelity and a pretty complex computation. So that is sort of the capabilities of our system currently. And so I'm going to now talk a little bit about architecture in quantum computer design. And we sort of got into this by looking at the 5-qubit cloud quantum computer that was put online by IBM a few months ago. So if you haven't looked at this, I highly encourage you to take a look. I mean, it's really a fantastic system. It's very instructive if you're teaching a class or if you're learning about quantum computing or if you just want to try out some circuits. Basically, what they've done is they have connected their physical quantum computer. So they have superconducting qubits. Each of these squares is like a superconducting island. They're connected with microwave resonators. And they've handed over control of this to an automated system that's connected to a website. So anyone can basically set up a circuit and run it on their physical device, which is pretty extraordinary. So the way this is set up is you have 5 qubits, and those 5 qubits are connected in the following way. So the gates that are available are CNOT gates that have this central qubit as the target. So that connectivity graph that this system gives you is star-shaped. Star-shaped because it has sort of one central point. And the gate set is this here, CNOTs. These are the 4 CNOTs, plus this gate library. They have these fixed individual qubit rotations. That's called the Clifford plus T library. And this is in contrast to what I showed you up to now, which is our ion trap system, which has full connectivity. And our gate set is this R and XX gates. And this is a more expressive gate library because it has all these continuous parameters in it that make it somewhat more flexible. But the main point is that we have this connectivity while this is a star-shaped system. And to show sort of, I mean, you could ask, does this matter at all? I mean, you know, you can still do any computation you like on this system, same as here. Does it matter at all? So I'm going to just show a few examples of circuits that we've run on both systems. And the first is 2 computational gates. And this is the Toffoli gate. The Toffoli is basically a controlled NOT. That means if the first 2 qubits are 1, it flips the 3rd qubit. This is basically this action. The Margolis gate is sort of a poor man's Toffoli, if you like. It's similar to the Toffoli, except it has this phase factor over here. And that means it's easier to implement, but of course, in general, it leaves sort of an entangled phase. And in a general quantum computing context, it's less useful. But it has the advantage that it has a much simpler circuit. You can see this is sort of the high-level circuit for the Margolis gate. It has 3 C0 gates, and crucially, they all connect to the same target qubit. So it maps very well to a star-shaped graph. So we run this on both systems. You can see they both do it reasonably well. And both need 3 2-qubit gates, 3 of their native 2-qubit gates to run it. Now, in order to run this on the 2 systems, what we've done is we've taken these high-level systems and circuits, broken them down into native gates, and then optimized it to minimize the number of gates on each system. So this is the Margolis gate. The Toffoli, on the other hand, you can see it has more gates. And crucially, they don't all connect to the same qubit. So for the ion trap, again, we lose a little bit of fidelity because we have to do these additional gates. And we can do this with 5 2-qubit gates. You can ask, why is it 5, even though there's like 6 C0s here? This is another advantage of having this XX gate available, because the XX gate has this conditional, so this continuous parameter, which means we can't just do a C0 gate, we can also do square root of C0. And that is additional flexibility, and if you have the square root of C0 available, you can do the Toffoli with just 5 2-qubit gates. So the fidelity drops a little bit because of this sort of overhead, but if you do it on a star-shaped system, you can see the result is a little lower, and this is because you need 10 2-qubit gates to do a Toffoli on the system. And that's simply because in order to do these here, you need some additional swap operations to be able to implement this. Okay, the second set of examples is 2 algorithms, and they are sort of textbook quantum algorithms, if you like. They're oracle algorithms. So there's an oracle that implements a function that has some hidden property, and you're trying to find out what this property is. So in the case of the Bernstein-Mazurani algorithm, we have this function, which is c.x. So c is like a 4-bit binary number. You do this sort of action. You're trying to find out what is c. So classically, you would have to put in several different input states until you figure out what c is, what those 4 numbers are. In quantum mechanics, we can just run this with a superposition of all input states and interfere the outputs to find c in a single shot. Now, the way this works is we have this ancilla here, which is, starts in 0, -1, and whenever there's a C0, it basically does a phase kickback onto these qubits over here that leads to them being rotated appropriately. So the way we implement these different oracles is basically by the presence or absence of these C0 gates. So if all these C's are 0, there's no C0 gates. If they're all 1, all of the C0 gates are here. And that way we can implement all possible oracles on this system. Okay, the second oracle algorithm is the hidden shift algorithm. Very similar concept, but the function now implements a hidden shift, which means the function is known, but the shift is unknown. And for a certain class of functions, there's an efficient quantum algorithm to solve this. We use the following example as a function, x1, x2 plus x3, x4. And this is the circuit that implements this function by giving you a phase factor with the function evaluation here. And the way the algorithm works is very similar to Bernstein-Mazurani. We run the oracle. So here the oracle you can see in the middle is the function, and it is embedded in this sort of shift pattern. So the presence and absence of these x's indicates which shift pattern is implemented. So in this case, 1, 0, 1, 1. And then this is interfered with the known unshifted version of the function, and the result, again, is the shift s in a single shot. Okay, so now onto the actual data. Again, we implement this on both systems. The Bernstein-Mazurani, this is the circuit again. You can see it maps very well to a star-shaped architecture because all the targets are on the same qubit. And if we run this on both, this is the outcome. You can see this is for all the possible oracles, and you basically get this diagonal, which means a one-to-one correspondence between oracle state and detected state. And this is done with up to 4 qubit gates on both, depending on which oracle is implemented. Now, for the hidden shift, you can see we have these 2 disconnected pairs of qubits, which means additional swap gates will be necessary for a star-shaped architecture, while for the fully connected system, we just do 4 gates again. It looks very similar. It's flatter now because it's 4 gates every time. The star-shaped system has to do additional swap overheads again, has to do 10 gates, and as a result, the fidelity is somewhat lower. Okay, so these were sort of the examples to show that it does matter what your connectivity is. This is sort of a theoretical overview of different connectivities. And what these arrows indicate is what is for a generic circuit, what is the overhead that you can expect by going from one connectivity to another. This is fully connected, which is sort of the highest connectivity possible, 3D, 2D, square lattice, linear nearest neighbor, and so on. So this is for a general circuit, but of course, in practice, it depends on what circuit you're running. So you can see, for example, a linear nearest neighbor architecture would map very well to this circuit because it's, has just two neighboring interactions. While here, a linear nearest neighbor would have a lot of swap gates, while a star-shaped one is fine here. But this is just to say that in general, it does matter what your connectivity is, and more connectivity is advantageous. Now, so this looks like a pretty simple story, right? I mean, it's sort of a juicy headline. We have beaten the IBM quantum computer and so on, which is totally not the message. It's because, just to remind you, these are two 5-qubit quantum computers. They can do nothing that you can't do on a piece of paper rather efficiently. So if I were to brag about it, it's like bragging about winning like a bubble blowing contest at a 5-year-old's birthday party. I mean, it is, you can say great, but it's, it's not very relevant beyond the present rather limited context, right? So what the future has to be is to scale up these systems. And in general, it will be true that no system, I have to disappoint some fans of the ion trap now, no system, including the ion trap, will be fully connected for very large n. Right? And for ion traps, we have a certain limitation, and that is, I showed you how we do 2-qubit gates. We do it by using the motion. And so if I make this longer and longer, this chain, what happens is more and more modes will come in. It'll be more complicated to control, and it will be slower. Because if you imagine like phonons moving from here to here, until this guy knows that motion has been initiated by this guy, it will take longer and longer for a longer and longer chain. So at some point, and we don't know exactly where this is, I mean, we're doing 5, fine, 10 is probably going to be fine. But at some point, probably below 100, at some point, there'll be a point where it's not worth it anymore to just put more ions in the same trap. And so you need to play additional tricks. And here's sort of a couple of papers that discuss this. Ion traps, we can shuttle ions around. So we could have ions that move, and then we can have another fully connected chunk over here. This means a larger system is not going to be fully connected, but it's still going to be reasonably densely connected. So this is fully connected, and so is this, but there's some sort of sparse connectivity in the middle. And additional, at some point, a module of ions is going to come to its limits, and then we can employ, for example, entangled phonons to connect distant modules to each other. And there's another experiment in Chris's lab that explores this aspect. But again, this poses a challenge, which I call the compilation challenge. And that is, of course, how do you optimally map your quantum algorithm that you want to run onto a system like this? Because, of course, we have all these quantum gates that I said, but in addition, you have choices to make. How many do you put in a group like this? Where do you split it up? At what point in the computation do you shuttle it? When do you bring in a connected state to a different module, and so on. So compiling a large-scale system like this is a considerable challenge. And this is why I think what this sort of points to, this sort of thoughts about architecture, is that going forward, we have to find some kind of method to co-design the hardware, the compilation structure, and the application that we want to run in one system to make it possible to scale up to a larger system. Okay. That's sort of all I wanted to say. This is to just showing you everyone who was involved in this work. This is sort of the crew in the lab. Shantanu, who's just defended his thesis last week. Kevin and Caroline are PhD students. Ken Wright, who has programmed the experimental control system that we rely on a daily basis. Our collaborators, Dmitry Maslov, who is a computer scientist doing quantum circuit optimization, and Martin Rötteler from Microsoft. He helped us with interfacing with the IBM system and running circuits on their machine. And of course, Chris Monroe. Thank you very much.
Thank you very much. Unfortunately, in the current 24-second news cycle, you only have 6 seconds to get the message out, 12 for analysis and 6 for rebuttal. So beat IBM is going to be the way it's going. Who would like to start with questions?
So the connectivity, it seems like for trapped ions that might be especially unscalable, where as you put more ions in a linear trap, the connectivity doesn't
Well, I mean, it scales, so there's going to be a sort of a roll-off of connectivity as you go up, right? But we start with a very good connectivity. While other systems that are sort of have a different connectivity, you might start with, in the case of the IBM, you start with a star-shaped connectivity, which is sort of the worst possible one. Linear nearest neighbor is slightly better. This is a lot of sort of solid state or semiconductor quantum dot implementations have a linear connectivity. But it is true, I guess, that this advantage is most obvious for small systems, which is the system we currently have. Yeah? And I wouldn't say it scales unfavorably, because even in a large system, you'll have local sections that are fully connected. And I think that'll always be an advantage.
Yes.
So you mentioned this IBM system that can only do 3-4 gates?
Yes.
Could you repeat the question?
So, so the question is, can they only do Clifford gates in the IBM system? So the Clifford gate, what they present to you as the user is they give you this Clifford plus T library. I think they can also do controlled roots of Pauli's in general, but they don't. No, a T is a Z rotation by pi over 8.
Oh, so that's universal, okay.
Yeah, it is universal, that's right. But it is not an arbitrary rotation. So this is one of the reasons why we did not implement the QFT5 on their system. It's because it doesn't map well with these, by not having continuous rotation. So you need a lot of pulses to approximate certain operations.
Do you actually know why they count arbitrary R theta rotation?
I think they can in general. Maybe it's harder to calibrate. They just don't present it to the user at the moment. But I think maybe they will do it in the future. But if they had it available, then they could do the QFT5. It would take about 30 gates, 32 qubit gates to do.
Did you have one?
Yeah, so in terms of finding the pulse solutions, the speed of each of the ions was inherently different. You saw it in the Rabi-Flavin curve, right? The ones at the ends were
For each of the
slower,
modes.
presumably because the light falls off at the end of the chain.
No.
Is that not a Gaussian beam?
No. So what happens is the modes that are where the detuning is the smallest are the modes that are most excited, and so they do the biggest loop in phase space. It doesn't mean that more distant ions are generally weaker. In fact, our best gate, or fastest gate, is currently the 1-5 gate, because the 1-5 gate, they have this sort of interaction, have this mode, which is both of these ions couple very strongly to. And so that actually is our fastest gate, if you like, at the moment, or our strongest gate. But of course, as you make the chain longer, this will get slower.
Yeah, my question was going to be, does that affect how you find the pulse solution? So obviously the answer is yes.
Yes, that's right. This is the main issue in finding the pulse solutions, is that different modes interact at different sort of strengths, or they do these loops at different rates as you do the gate. And so you have to find some solution that closes them all at the end.
Vlad, did you have something?
Yeah, I'm curious, what's the prospects of remote entanglement gates, including
So that will.
Could you repeat the question?
The question is, what is the prospect of doing this remote entanglement that I've sort of mentioned at the end for scalability? And so there has been, like I said, there's a lab in Chris's group that actually just deals with this aspect, and they have sort of increased by 3 orders of magnitude the rate of entanglement that they can generate, but it's still reasonably slow. It's like a few hundred hertz, or maybe the experts are here. So in order for this to be sort of, usefully employed, probably another couple of orders of magnitude are necessary, so that the remote entanglement rate is not terribly much slower than the rate of a normal 2-qubit gate. So these have to be comparable in order to make it a useful resource, I think.
Well, stop by and see Norbert at lunch today, and thanks again.
Thank you.
Next up is Dong-Ling Deng from the Center for Condensed Matter Theory. He is a graduate, he's got his PhD from the University of Michigan under the supervision of Lu-Ming Duan, someone well known here, and joined us in May of 2015. And he's going to talk about the ever popular subject of many-body localization.
Is there some button?
Macintosh users, please unite.
Oh, is this correct?
Yeah, that's what I used just now.
Always call a theorist when you're having trouble.
But this still doesn't show up.
This theorist will fix that too.
How did they?
It's not quite as easy as it looks, by the way.
Okay, thanks, Chair. Okay, thank you, Chair, for the nice introduction, and thank you for giving me this opportunity. Good morning, everyone. Today, I'm going to talk about exponential orthogonality catastrophe and the logarithmic lightcone in Manybody localized system. This work is a collaboration with Xiaopeng Li, Jed Pixley, and Yang Wu, and Professor Shankar Sama. In this talk, I will only briefly introduce the basic ideas and present the main results. If you are interested, please go to those two papers for the details. Oh, yeah, here. So today, we will consider a very simple one-dimensional system with random onset potential. So the Hamiltonian describing this system is a one-dimensional Anderson model. So here, this J describes the hopping strength between nearest neighbor sites, and this U describes the interacting terms. And the A dagger are the annihilation correlation fermion operators, and this N is the Fermi number operators. And this mu J describes the onset random potential, which is drawn from independently from a uniform random distribution. In this talk, we will only focus on the localized regime, which means we have a very strong random disorder. And by localization, I mean that the system do not have any charge conductance or thermal conductance even at the finite temperature. So, and we quench the Hamiltonian by adding a local onset potential, repulsive onset potential at site 0. So to arrive at a final Hamiltonian HF, I will ask two questions. The first question is more about the static properties of the final Hamiltonian HF. I will ask, will this local perturbation on this set 0 induce a orthogonality catastrophe or not? The second question is more about the dynamics of this post-quench dynamics. I will ask, how fast can information propagate in this localized system? So for the first question, I will give a positive answer. I will show that in localized system, there are indeed an orthogonality catastrophe, but there are two new features. The first one is that this orthogonality catastrophe in localized system is exponential decay with system size. And the second one is that this orthogonality catastrophe is statistical, as I will explain later. For the second question, I will show that information can only propagate logarithmically in time in this localized system. Okay. So let's go to the first part, the orthogonality catastrophe. Let's start with Anderson orthogonality catastrophe. So consider a metal. We're shedding an X-ray to this metal. This X-ray will kick out an electron from the valence band. And then all the electrons in the conducting band will respond to this cohort left by the X-ray. And then each single particle of this, each single particle wave function of this electron in this conduction band will respond to this. And we'll get a small phase shift. But there are a huge number of electrons in the conducting band. So that leads to a drastic change of the Manybody wave function. And this phenomena is first shown by Anderson in 1967. So in that paper, he showed that if we, for a metallic system, if we add a local perturbation to the system, then the ground state, the new ground state, the overlap between the new ground state and the initial ground state will have a power law decay with the system size. Here, this gamma is some positive number related to the phase shift due to this cohort. As you can see, in the thermodynamic limit, this error goes to infinite. So then this wave function overlap will go to 0. That means the new ground state is orthogonal to the original one. So that is a well-known Anderson orthogonality catastrophe. So, and Anderson orthogonality catastrophe has many important consequences. For instance, it explains the power law X-ray singularity problem, and also it leads to a power law decay of the logarithmic echo. This logarithmic echo, which can be experimentally observed, experimentally measured in called atomic systems. But all this Anderson orthogonality catastrophe is about a metallic system, which where the wave functions are extended. So then, what will happen in a localized system? Intuitively, we expect there nothing gonna change drastically in localized system because the system is localized. However, as I will show that in localized system, actually there is exponential orthogonality catastrophe. In some sense, it is even stronger than the Anderson case. So, because here we consider random samples, we will do an average, geometric average over these random samples over the wave functions. Then and define a typical wave function overlap f tip. And we will see that this typical wave function overlap will have an exponential decay with the system size. Here, this beta is some positive number. And this L is the system size. So you can see in the thermodynamic limit, this L goes to infinite, and this typical wave function overlap will also go to 0. So that means the typical wave function is orthogonal to the original wave function. Okay. In order to study this exponential orthogonality catastrophe, we did some numerics. So we diagonalized the initial Hamiltonian HI in the HF to find out the ground state, and we then calculate the ground state overlap, and then we do a geometrical average on this wave function overlap. As you can see from these two figures, this figure 1 is without interaction. So as you can see, it's indeed this log f averaged has a linear scale with system size. That means the typical wave function overlap has an exponential decay with system size. And we also did some exact diagonalization for the interacting case. We can also see the linear scaling with system size. That means we indeed have exponential orthogonality catastrophe. Then how to understand these results? So let's get some intuition from the non-interacting limit. In the non-interacting limit case, for the ground state of a Manybody system is just a state with all the particles just occupy the lowest single particle eigenmodes. So then imagine we add this local perturbation slowly enough such that the system is always in the ground state. Then as you add this local perturbation, there will be a bunch of avoided level crossing for these single particle wave functions. If we do this slow enough, then we will, in the adiabatic limit, then this charge on the side 0 will be transferred to some other side. So this will give us, because this charge is transferred to some other side, then this will give us orthogonality catastrophe. So as you can see from this charge transfer picture, this orthogonality catastrophe here is statistical. That means it depends on the random realizations of the samples. As you can see also from this figure. So let's set our chemical potential to 0. If initially the onset potential of the set 0 is larger than 0, that means there is no particle occupying the set 0. Then after you add the perturbation, there is no charge transfer, and as a result, there is no orthogonality catastrophe. There is another case which there also will be no charge transfer. That is, if the onset potential at set 0 is too small, then such that after even we add this perturbation, the onset potential in the set 0 is still smaller than 0. That means there will be still a particle occupy set 0. In this case, there will also be no orthogonality catastrophe. The only case that there will be orthogonality catastrophe is in this region. When we add the perturbation, then the onset potential on set 0 is larger than 0, then there is a charge transfer. Then correspondingly, there is a orthogonality catastrophe. So the orthogonality catastrophe in these localized systems are also statistical. Now let's do some simple math to understand why is exponential decay with the system size. So we also want to get some intuitions from the non-interacting case. For the non-interacting case, all the single particle wave functions are exponentially localized near the localization center. Here, xn is the localization center, and the kc is some localization length, single particle localization length. Then for a certain disorder realization, as I explained, there will be a charge transferred from set 0 to some arbitrary set Rf. Then the leading contribution to the overlap will be just the overlap between these two localized single particle wave functions. And this overlap between those two single particle wave functions has an exponential scaling with Rf. Then after we average our random disorders, because our random disorder is chosen uniformly from uniformly, then this after we average this RF will have a linear scaling with the system size L. So then if we do a geometric average over this F, basically we take a log over the F and then do the random average, then we will get that the typical overlap wave function overlap has a exponential scaling with the system size L. As I explained, this beta is a positive number. It's equals to P over 4 kc. Here P is the probability of the charge transfer. And this 4 is due to that the average distance over the charge transfer is 1 to the 4th over the system size. Okay, so now let's go to the second part. The second part is more about the dynamics of the post-quench dynamics about the logarithmic entanglement lightcone. So as we all know, in spatial and general relativity, Einstein told us that the speed of information is limited by the speed of light. Then this gives us basically a linear lightcone. In quantum Manybody system, there is an emergent analog of the speed of light. This was first discovered by Lieb and Robertson in 1972. In their paper, in their paper, they basically developed the well-known Lieb-Robertson band. Let's consider a simple one-dimensional system. We consider a local operator A, which is supported at some local region X, and another operator B, which is supported in some region Y. And we denote the distance between these two local regions as the dxy. Then Lieb and Robertson were able to derive this famous inequality. Here, this double vertical line means the operator norm, and the C and the eta are some constant numbers, positive constant numbers. And this V is the so-called Lieb-Robertson velocity, which is an analog of the speed of light. So if by requiring this D equals to Vt, we can extract linear lightcone here. Basically, this tells us if some event happened locally here, the influence of this event can at most propagate linearly in time. This gives us the linear lightcone. So this linear lightcone, very interestingly, this linear lightcone has already been observed in many experiments, especially here in the beautiful experiment carried out by Chris Monroe's group. They showed that if you tune the exponent of the power law interaction in the trapped ion system large enough, then you will also get a linear lightcone in the ion traps. However, this linear lightcone is more about the delocalized system. It's an extended system. What's going to happen in a localized system? So in the localized system, everything is localized. So in the single particle case, but there's some difference between the single particle localization and the Manybody particle localization. In the single particle localization case, it can be mathematically derived a zero velocity Lieb-Robson band, as shown here. This here C and eta are also some positive constant numbers. You can see this band is independent of time t. That means the information cannot spread out in these Anderson localized systems. Actually, there's recently a mathematical proof that there will be no entanglement growth in the Anderson localized system. That means no information can spread out. However, in the Manybody localized case, under some assumptions of local integrals of motion, people have derived that there is indeed a log t Lieb-Robson band, as shown here. So, as I said, this C and the eta are also some positive constant numbers, and this alpha is some also positive constant. And as you can see here, this information can only propagate out logarithmically in time. So this gives us a possible logarithmic lightcone. However, as I have said, this band is derived from some unproven assumptions, basically the local integrals of motion for the Manybody localized system. And another question is that whether this band can be saturated or not. So in order to study all those questions, we did some numerics. So we studied the entanglement dynamics after the quench. So basically, we start with an eigenstate phi I of the original Hamiltonian Hi, and then evolve it under the post-quench Hamiltonian HF. And we can consider the entanglement dynamics. We cut the system into two parts, R and Q. And we calculate the von Neumann entanglement entropy, which is shown here. Here, this rho R is the reduced density matrix, of this subsystem R. And in our numerics, in order to calculate the eigenstate, we use the DMRG technique. And then we use the TBD to do the time evolution. One thing I want to emphasize is that the DMRG here is different from the conventional DMRG. In the conventional DMRG case, we only care about the ground state. But here we need to calculate all the excited eigenstates. So it is different. So after we calculate this entanglement dynamics, we calculate the entanglement entropy for different cuts. Basically, we cut the system into differently into two parts. And we calculate the time dependence of this entanglement entropy for the different cuts. The result is shown here. So as you can see, there are indeed some entanglement growth after some time. For instance, for this cut, far from the perturbation xc equals to 4, it will take longer for the entanglement to grow. So then, if we find out when will this entanglement for a specific cut will grow, then we can extract a logarithmic lightcone, as shown here. So basically, this is showing by find out when the entanglement entropy for a specific cut will grow. Okay. So I want to emphasize that this result, our result, is derived directly from the numerical data. So there is no assumption. And also, as shown here, the entanglement has a logarithmic growth. That means the information is indeed spread out the whole system. This indicates that the log T Lieber-Robertson band cannot be further tightened to a constant band in time. So that shows the difference between the many-body localization case and the single particle localization case. Okay. Okay, here's my summary. So in this talk, I briefly introduced an exponential orthogonality catastrophe for localized system. I introduced a non-local charge transfer picture to explain this exponential orthogonality catastrophe. I also briefly introduced a logarithmic entanglement lightcone. In the future, it will be extremely interesting if those exotic phenomena can be observed in experiment. The take-home message is that in localized system, there is an exponential statistical orthogonality catastrophe and a logarithmic lightcone. Okay, that's all. Thank you.
Thank you. Questions?
Yeah.
Yes.
So it seems that you are working on the one-dimensional things for orthogonality, catastrophe, and the Lieber-Robertson band. So do you have any idea in higher dimension, like 2 or 3?
Yeah, good question. The question is that I only consider 1D. Is there any result for 2D or higher dimensional system? Indeed, I will think about this. However, the problem is that in higher dimension, it is hard to numerically calculate this entanglement entropy, and also it is hard to calculate this eigenstate, the time evolution, etc., etc. Yeah.
Yes, Alexei.
There seems to be a huge difference between having this log T in there and not having it. In one case, it doesn't change time at all. In the other case, it sort of basically grows to infinity as a function of time. So is there any prospect for proving this? I mean, it seems like it should be.
Yes, a good question. Yeah. So the question is that is there any proof? Is it possible to mathematically prove the log T Lieber-Robertson band? Yeah, I have discussed this with Sean a lot. I think from inverse proof, if we do not make any assumption, then the only possible way is to go from the inverse proof. However, the problem is that it is very difficult to take care of the real resonant event. So in the many-body localized case, there will always be some resonant pairs which look far away from each other. So it is very hard to take care of those events, although the probability is very small.
Yeah. For this logarithmic lightcone, since you are doing numerics, how can you rule out the cases if you wait for long enough time and actually saturate?
Yeah, that's a good question. Indeed. So the question is that how can I how can I know whether the entanglement entropy will saturate or not in the long time limit? Yeah, in our numerics, we only did TEBD calculation. That means the Barron dimension I can do is always limited to like 30 or 40. So in this case, we cannot deal with the long time limit case. However, we also have some exact diagonalization results. In our paper, we showed that by exact diagonalization, we show that even in the very long time limit, there's still some entanglement growth far away from this local quench. Yeah.
Was there one back there?
Yeah.
The bound you show was for the solar average case.
Yes.
Do you have any idea of how much it deviates in some random implementation?
So yeah, so good question. So the question is that do you have any idea about the variations of random samples, right? I think there are some variations. However, I mean, this is a Manybody problem. It is hard to mathematically deal with it. I think there should be some variations, but just too hard to do it. Yeah.
Anyone like to have the last word? Well, if all is said and done, let's thank both speakers.
Thank you.